All right, so let's get started. I'd like to bring this back up from last time really quick. Remember we closed last Thursday on we were running this. We basically walked through a case study of optimizing a program, and if you remember the program, it was this numerical program where what we did was we divided the program into various phases, and I'll just page it back in for you. I said on phase 1 we're going to update all of these black cells in a grid, and we updated every black cell by looking at the neighbors. And then we said, hold up, wait till everybody does their work. Everybody's got to check to see if convergent, so we're supposed to stop. And then we're going to repeat the next iteration if we haven't converged. And the last thing that all of you did in class, like our last 3 or 4 minutes of class last time, was you all told me why there were 3 barriers in this code. Okay, and it's just a quick review. Remember, all of the threads computed some elements and computed how much did they change the final output. And then all of those threads accumulated their partial sums into a variable. And then if that variable exceeded some value, if we hadn't converged, all the threads just went back to the top of the loop again and continued. Okay. And we had a number of barriers in there. We said, well, this barrier is here because all the threads need to know that all other threads have accumulated into this sum, so it's the final value before we check if we're going to continue. That was why we had this barrier. And then we had this barrier because we were like, well, wait a minute here. We need to make sure that everybody has checked the actual value to determine if they should continue before any thread gets to the top of the loop again and resets those values. And then there was even a third barrier which says, well, we need to prevent anybody from going through this section of the code and actually updating that value perhaps before it got reset or something like that, or checked by someone else. So there were these 3 barriers. And I asked, did anybody, and maybe you posted this on the website, did anybody come up with a way to do this with 1? Nobody puzzled over this, because this would be a good thing to talk about. So let me just give you, what is the reason why we have to keep waiting here? There's a variable that we keep checking, right? And what's that variable? That's mydiff. And what does mydiff do? Mydiff is a single variable that holds the value of the amount of change per iteration. And the problem that we have is that this is code with multiple iterations, and that mydiff value is being reused over and over again to represent the change in each of these iterations. So the problem is that all these threads have to get out of iteration I before anybody can start doing any work with mydiff on iteration I plus 1, right? So why not just have different variables for all the different iterations? If all we do is have a different variable, if we had mydiff for iteration I, everybody would, in iteration I, would just accumulate into the iteration I version of mydiff, check that, and then you don't have to wait at all, because when you move on to the next iteration, you're starting with a different variable, or you're reading and writing to a different variable. So this was a case where I have kind of falsely created a dependency in the program that didn't need to be there, because I was reusing one variable for a couple of different purposes, every iteration. So a very simple solution would be to go to one barrier here, and instead take this diff variable and make it an array. Now conceptually what I've done is I could have made a different array of size, diff is an array of size number of iterations, but really all I needed 3 different copies of diff. I need to maintain a diff from the last iteration, the current iteration, and the next iteration, because all threads are only going to be kind of in one of those 3 iterations. They're either finishing up from last time, working on the present, or trying to move forward to the next. So what I did is I just said, I'm just going to duplicate that variable and make sure that the accumulation goes into the right copy of the variable every time. So this is kind of like the same idea as what we did right here, where we had that one single variable mydiff, and remember we made a local copy of it to accumulate our partial sum. So that was, again, the same technique. It's like we had one copy of a variable and everybody was synchronizing on it. So we said conceptually, everybody can write to a different copy of the variable and we can get things all synced up at the end. So that was just, it's interesting. It's actually the same trick, just used in a different context. Okay. So at the beginning of week 3, let's finally start talking about some program optimization techniques. And the way this work is going to go, the way this week is going to go, is today I want to talk about assignment, or ideas for how to figure out what thread or what worker does each piece of work. So today is going to be about workload assignment and scheduling. And then Thursday is going to be about doing that scheduling in a manner that reduces communication costs, reduces stalls due to memory and stuff like that. So today is going to be about, we're not going to think much about memory at all. We're just going to think about synchronizing a bunch of workers and making sure everybody has a good workload balance. Thursday, it's going to be about, let's make sure we're communicating and accessing memory efficiently. Okay? So here's where we're going with this. Okay. So, and yeah. My first disclaimer before we get into any of the work this week, and even next week, we're going to now start telling you about strategies for scheduling programs efficiently. And I cannot overemphasize, and case 1 being your assignments, and in particular, this is going to be true in assignment 3, is people go, oh, I heard about these complex, all these ideas in lecture. I'm going to think about the problem that they give me on my programming assignments, and I'm going to figure out how to apply some of the more advanced techniques. And without question, I want you to take a different approach. I want you to take the simplest possible approach that gets the program working, and then the simplest possible approach to parallelize it. And I want you to measure your performance. I want you to do the types of things that we forced you to do on assignment 1. Put in some timers, figure out which thread is doing the most work, those kinds of things. And then only if performance is bad do you start doing something more sophisticated. Okay? And this is the case. This happens every year to, I would say, about 10% of students in the class. They read the handout. They read the lectures. They get on the whiteboard and they come up with a pretty sophisticated scheme to solve the assignment. And they do that for multiple days. And then they say 3 or 4 days before the assignment is due, they're like, we're just going to code it up. As soon as we can get it to work, it'll be great. And it turns out often that their complex scheme is slower than a simple scheme. Okay, so always do the simple thing first and use measurements, use data to govern what you do next. Okay? So I'm going to start with the simplest thing here. And the next sequence of slides is going to all be about balancing work. And the name of the game when you need to balance work, here's an example where I have 4 processor cores. And for whatever reason, one of these cores, processor 4 here, core 4, does a lot more work than the others. And the reason why that limits speed up is we have effectively serialized parts of our program. A large part of execution time, only one of these workers is doing anything. It is effectively running as a serial program. So if you have a bunch of work, and you have a bunch of cores or threads, whatnot, what is probably the simplest way to divide work onto those workers? Or in other words, where do we start on program 1 of assignment 1?
Just give each of them a contiguous chunk of the workload.
Just give everybody an equal. I'm not even going to think about what's contiguous or not. But we did something like this. We said, we're just going to break up the work completely evenly. Now we need to kind of dig in a little bit on what we mean by even. So on program 1, evenly meant same number of pixels, right? And so here are a couple of different strategies for breaking that work up. So this was the original version of assignment 1. If these were actually pixel-sized rows, you might have ended up with a solution that looked a little bit like this. If I didn't make the constraint that said your solution should probably work for any viewpoint, you might have done something like this, where you just kind of manually said, okay, I kind of know what the expense of every pixel was, and therefore, I divided up the work equally. Now, in these diagrams, actually, how do I know how much work is associated with a pixel? One of the reasons why we use this as a starting example is that it's pretty clear. Yeah, the brightness of the pixel is kind of how expensive it is to compute. So, the regions down here are not a lot of work. The regions in here are a lot of work. And as a result, this scheme yielded a significant amount of workload imbalance, right? Now, some of you decided to come up with a solution where you interleaved the assignment of pixels, rows of pixels, to the output, or to the threads. And why is that actually an okay solution? Because each of those rows has different amounts of work, for sure, right? Different regions of the image have very different amounts of work. So why did that actually work out pretty well? Yeah.
Because on average, there's always one thread getting started with most of the work decrease because they're interleaved.
And we're kind of assuming that rows right next to each other kind of have the same amount of work because there's kind of some continuity to the figure. So if every really local piece of the image gets divided up into 4 rows and go to different processors, that means all the processors on average will end up having a reasonable amount of work. Now you could imagine a different workload where that would have been a terrible strategy. For example, imagine it was all white at the top and then slowly went down this way or something like that. The top half was a triangle. That would mean that processor or thread 1 would always get a little bit more work than thread 2, which would always get a little bit more work than thread 3. But in this case, it actually turned out to be pretty good. So what are some situations where you think you can pull off this, and the title of the slide is static assignment. In other words, you can go, without ever actually looking at the execution characteristics of the program, I can kind of just say, if you give me the size of the image, if you give me the number of workers I have, I'll give you a scheme that's always going to be pretty good. So what are the properties of this that we knew about?
I guess you have to know what parts of the program are going to be more intensive than other parts.
This would have been very easy if all pixels were the same cost. Okay, so you have to have some ability to predict the cost of things. In this particular case, you actually can't really predict the cost of any one pixel, but you definitely can predict on average that stuff is going to be about the same. So there's this notion of predictability that kind of makes this problem pretty easy. Right? You can just say, well, if I have 8 threads or so many threads and I have this many pixels, here's a way I can just describe the policy up front for who does what, and I'm going to get a pretty good workload balance. I'm going to schedule this out onto the machine, right? So this is really applicable when the cost of the chunks of work, and here the cost of the work is maybe the vertical height of these bars, is equal. If I know I have 12 pieces of work and they all have equal time and I have 4 different workers, 4 processors, sure, I might just divide 12 by 3 or 12 by 4 and I get 3 pieces of work per worker. Really simple way of doing it. And this is great because once I tell P1 and P2, you're responsible for the first quarter, you're responsible for the second quarter, these threads don't have to synchronize. There's no communication. They can compute what they have to do without knowing what anybody else is doing. And that's very helpful because it minimizes communication amongst the threads. Static assignment, as we saw in that fractal example, can also be applicable when you don't know the actual cost of any one piece of work, but you know that on average, you're going to end up with, on average, everything is the same. It might have some variance. And if I give enough jobs to every worker, if I add up the length of the dark blue bars and plot them like this and stack them, all the different threads end up getting about the same amount of work. So here's an example where on average everything is the same. And just because there's variance, that doesn't mean that I don't get a good workload balance from a simple just chop it all up strategy. Okay, and that fractal was a good example. There are a lot of applications, especially if you anything that runs for a long time. Let's say you're a supercomputing simulation. This is a figure from a turbulent simulation. What you see here in white is actually the profile of a wing. So you're actually looking down at the edge of the wing, like towards the fuselage. And this is a mesh that's discretized all of the fluid flow around the wing. And so you can see that super high resolution around here. That's actually because you need high resolution around areas of high pressure. And the coloring suggests what cells of the mesh are processed by what thread. So different colors. So in space, there are very different amounts of space per thread, but probably if we look carefully and counted the number of cells per thread, it'd probably be about the same. Okay? And you can imagine that, like, if we're simulating this airline, this wing for like a long period of time, maybe during takeoff or landing, or as the wing geometry changed, if the distribution might change. So it would be perfectly fine if, for example, we decided to go with a static assignment of grid cells to the threads at the beginning of the program. Maybe we let it run for a minute or two, and then maybe the pressure changes, and we have to update the number of cells. And then we do another assignment again. So I like to, like there's this term semi-static assignment, as you can kind of think about it as, given the state of the world, I'm going to upfront assign work to workers, and then I'm not going to change that assignment for some amount of time. So I just want people to not walk away going, static assignment means it's like sort of known at compile time when you write the program or something like that. Okay. Another good one would be, any kind of long-running machine learning computation. You might run that training for a while, understand where you have some workload imbalance, adjust that workload imbalance, and then run again for another hour, and so on and so on. Now, the flip side of static assignment would be to do the assignment dynamically as we go. So let's say that we cannot predict the amount of time that a task might take. It might be very short. It might be very, very long. So there's not really any way we can upfront say, okay, you are going to do all these, and you are going to do all these. Okay. So here's an example program. I wrote it in just kind of pseudocode. Imagine there's a void main. And then here's a sequential program for I equals 0 to n. I want to compute whether or not some number in the input array is prime, which is something that's a little bit harder to predict how expensive that would be, for example. And now imagine that I have a version of this code that runs in an SPMD fashion, not necessarily written in ISPC, but it runs in the SPMD programming model, which means however many threads I'm running in my program, they're all running this code, and they just have a different thread ID or something like that. So imagine that in the parallel version of this code, there are n threads running this code. And the way my code works is all the threads continue. They just do their thing until all elements of the array have been processed. And the key thing here is there's a counter, and there's a lock on that counter. So the counter starts at 0 and counts up to n. And then every thread says, well, if I have nothing to do, grab the lock, increment the counter, and then whatever the counter's value is, I'm responsible for that number. So first of all, let's check to make sure that do all n elements of the array get processed? Yes. It would be bad if two threads did the same work. Is there any way for two threads to do the same work? No, and what ensures that that's the case? This lock here, right? So this lock says that no one else is going to be reading that counter while I'm incrementing it. So I'm guaranteed that I will perform that update, increment the counter. I'll take the current number. It's like basically a ticket at the deli counter or something like that. And then everybody coming later that looks for more work will get us a later number. And we're all going to get unique numbers, and as a result, we're going to do all the work. And does this code terminate? It will terminate because if a thread fails to get a number, it will quit. And once all threads have quit, we are done. Okay. So even though this is basically some C code with a lock and a counter, what have I really done here? If you were trying to sort of explain this in high-level terms on what is the work assignment strategy?
Yeah. It's basically just whichever thread is available, just give it work and keep doing that.
Yeah, so how does this program define the work to do?
basically defines it by whichever thread is available to do it.
That's how it's going to be. That defines how a thread is going to get assigned work. But I want what I'm looking for here is like, when you read this program, like first of all, how would you, if you looked at this program and talked to like your neighbor sitting right next to you, you would say like what's the definition of the work here? The work is to compute the primality of all of these numbers, right? And a single piece of work is what? Computing the primality of one number, right? And how does this program define all the work we need to do? Basically, it defines it via the current, basically the number n, right? The array and the number of n. So basically, I've said, look, there's a whole array of stuff to do, and we're going to divvy up that array by indices. And the way it's going to work is we're all just going to keep grabbing the next index that nobody else has done yet until they've all been done. And you might even want to say, like, effectively, even though you don't see a queue data structure or anything here, effectively, I've thrown all of the things I need to do into a big queue, and I've implemented the queue by an array and a counter. Right. So conceptually, this is kind of like, I have all this work, I threw all the work in a shared work queue, and I have a bunch of worker threads go into the queue and say, pop me the next one, pop me the next one. Now in this case, I have a very efficient implementation of that queue because I know all my data is stored in this array already. And I can implement, going back to the thing, I can implement queue pop by essentially just an atomic increment of that counter. So I'd like to make sure everybody, does that make sense? Right? Like conceptually, that's just a work queue and so on and so on. Okay. So this is like your canonical dynamic assignment thing, is you just expose all of the potentially parallel work that can be done in parallel. And then you let the underlying system dynamically assign work to your workers, to your threads, based on if anybody goes idle, they should probably do more work. Okay. Now, yeah. In program 3, a lot of people asked me this question about when I created these ISPC tasks, shouldn't I just create 8 tasks? I'm on a machine with 8 threads, right? And people are like, why the heck do I need to like create more tasks?
Not imperative. So you're saying that you can distribute it into this many different parallel units of execution, and then the emitted code can decide to do that parallelly to up to that extent whenever it wants.
And so if you just like cut this thing into tasks, and you cut it into 8 tasks, or let's just say you had a computer with four cores, haven't you just divided the work up into this? And what do we know that's wrong about this scheme? It's really unbalanced. Now, what if instead I cut this up into a bunch of pieces, not that scheme over there, but just into a bunch of smaller pieces, and then I throw all those pieces in a work queue? Those pieces are all of different cost, but why am I going to end up in a good place?
Yeah, because the program is better able to distribute the work. You don't have the issue.
Because like something like that might happen, right? Like, and as long as I have enough pieces of work, and they're relatively short, all those threads are just going to keep taking the next thing until they're ready, until everything is done. So what's the cost of this? Where am I? Of this dynamic scheme? Let's say under the hood, I replace n to be number of tasks, and is prime to test primality is run task I. What is the cost of the dynamic allocation here? What do you not have to do in programming assignment 1 or program 1?
We have to use the invoke. So
You don't have to synchronize.
Yeah.
Right. So the question is the good workload balance, the benefits of that compared to the cost of this, does it overcome the potential workload imbalance that you might have if you used a static allocation? And it turns out that in this case it certainly did, right? Okay, so that kind of gets to like what constitutes a piece of work, right? So in this program, like the unit of scheduling or the unit of assignment is what? It's one number, right? And so if I like plot this thing out, let's just think about this being time. And the vertical blue bars are like actually like imagine this is a plot of one thread. And the blue bars are like time that it's spent testing primality or running the ISPC task or something like that. And then the white bars are like time spent grabbing the lock, incrementing that counter, and getting out of the lock, right? So the question is, like, do we have a problem? How would you know? Yeah.
It would depend on how long it takes to do the synchronization compared to how long it takes to do each task.
Yeah, like another way to think about it would be, imagine I did this. I gave you this program, and I said, I want you to make it go as fast as you can. Are you done? What would be your next step in thinking about this? I gave you this program, and I said, are you done, or is there something better you could do? How would we go about even figuring out the answer to that question? Okay, get us started. I want to talk through this debugging exercise.
Yeah. We would first get timing for this program.
Okay, so let's say the first thing I do is I put a timer at the beginning, at the end, and it says it took 5.9 seconds. Okay, put a timer in the program.
What percentage of the program time is spent in the lock or waiting for the lock as opposed to...
Yeah, so the next thing I would do is I would put my timers right around test primality, and I would compute this. And then the difference between the timer around the whole thing and the sum of all of the timings of test primality is the overhead, right? I could also put my timer around the lock and do the opposite, but you get the point, right? So if I know how much time my program takes, and I know how much time I've spent doing useful work, what do I do next? I've got a lot of useful information now.
You basically want to compare it with, like, if you were to do a static assignment, like how much time the
So there's a couple of questions I could have. So first of all, I could implement the static version of the program, and hopefully I might have done that first. And I said, well, that's the speed I got. It was like, oh, it's like 8 seconds. So I'm like, okay, I'm already like 5.9 seconds. I'm doing better. But now my question is, can I do even better than the 5.9 seconds? And the information I have is the total 5.9 seconds. And let's say that I end up saying I spend 5.75 seconds in all of my calls to test primality. What do I conclude?
you probably can't really do better.
Yeah, you're like, well, like if 5.9 seconds is the whole computation, 5.75 seconds is like all the useful work. The only thing I could do is shave off like, 0.1 or something like that. And then I decide, if I'm a high frequency trader, maybe I have to win that race and maybe I go for it. But if I'm working on an assignment, I say, screw it, I'm going on to the next class. Like there's nothing much more I can do. Right, exactly. Now, if this timer around test primality says all calls to test primality are total maybe 2.5 seconds, now I'm like, well, wait a minute here. More than half my time is probably being spent elsewhere. And since this program's so simple, I know exactly where it's being spent. It's being spent in this lock. So what do I do next? Let's say my timers tell me over 50% of the time is spent in this lock. And I'm like, yeah, I wouldn't mind trying to make this thing 2 times faster.
Yeah. You could try a static assignment scheme for reasoning.
Okay, so one conclusion, like let's say this was my first program, and this would probably be a really simple program to write first. You could say maybe I don't need this dynamic mechanism. Maybe I should just back off and do a static assignment and remove that. That would be that would be a very viable strategy. There's a few simpler things I might try first that don't require me to rewrite everything. Yes, sir. Yeah.
Assign more than one prime number every time they get the lock.
Oh, okay. So what we did here is we said we're going to break this work up into the smallest pieces that are possible. Maybe okay. I'm sure you could parallelize inside the test primality, but we're not going to do that. Let's say this is a black box. And the reason why I divided things into the smallest pieces as possible was what? I didn't explicitly state that. Yeah.
It's like you want to have the smallest increment so that you have a better probability of getting like an even workload between threads.
Correct. Like, so the more little pieces I have, the easier it's going to be for me to come up with a partitioning where everybody has about the same amount of work. Imagine I only had, let's say there were 8 threads, and imagine I divided the work into 8 pieces, and I used a dynamic scheduling scheme. Not that helpful, right? So I do want a lot of pieces to give me the flexibility to arrive at a good workload balance. But the smaller I make those pieces, the larger this overhead potentially is, right? So I like this suggestion. Maybe if we just double the size of the pieces, we still have enough stuff to do. Because maybe, let's say n is like 1,000,000 and I only have 8 threads. So how would you implement taking 2 pieces of data out of the queue at once? Yeah.
You just increment counter by 2.
You just increment counter by 2. And what that's done is it's going to reduce the number of white bars here, or white regions here, by 2, right? And I could just play with that number. And I didn't do it by 2 in my example. I did it by granularity. I parameterized it because I'm a good software engineer. And I can mess with that parameter right before the deadline to get the best performance. And so I increased the granularity of my task to reduce overhead. And it's very likely on a lot of modern systems, like taking this small little increment is not that expensive. So most likely you probably can make your workload granularity with just making it a little bit bigger, can basically probably wash out the overheads in a lot of dynamic situations. So that's the trade-off. Like, we want as many tasks as we can get by with, or we want enough tasks that we can nicely schedule the work, but we don't want unnecessarily many tasks such that overhead got too high. For example, I don't know if any of you tried actually doing 1 task per row, like creating like 1,000 tasks. And at some point, you might have started to see the speed up curve fall off. You almost certainly would have seen it fall off if you made 1 task be a pixel. Yeah. So here's an example. Imagine I have these 16 tasks. So this is task 0, 1, 2, 3, all the way to 15 over there. And I just purposely made the last task much, much longer than the rest. Okay. Now imagine some dynamic scheduling approach, just like what we talked about. And here's a possible final assignment as a result of the dynamic scheduling. So notice that even though I did dynamic assignment, I got a little bit unlucky. Because the work at the end of the queue was actually really big stuff. So like the last piece of work that I assigned was like the longest running piece of work. And so I still ended up with like a long tail here. And there's some strategies you could try. Like if you happen to know a little bit more about your tasks, you might do something where you assign the biggest tasks first. So I'm going to take this, now look at the P4 got assigned the big task right at the end. If we actually decided to like sort things by cost, maybe I'll assign P4 the biggest task at the very beginning. And notice that P4 only does 2 tasks, but everybody kind of ends up finishing at about the same time. So the more you know about your tasks, the better you can do some scheduling. Now the other strategy we've talked about, and that was we just talked about it with these barriers, or that mydiff variable, was if we have a bunch of communication, what is being shared in the work queue example? So in the example that I just showed you with the pool of worker threads, the shared variable is the counter, is the lock and the counter. And maybe if we were running this on a big computer with like 128 threads or something like that, that contention for that counter might actually be pretty non-trivial for, especially if the work was small. Okay? So I want to get into a little bit more advanced mode on how you might alleviate the costs of having a shared work queue by actually distributing, making copies of that work queue for every thread. Okay? And so this is going to be the same idea as, remember, we took the single mydiff variable and made local copies of it. So you worked on your local mydiff and then only aggregated those results when you had to at the very end. We're going to do the same thing here for work queues. Now you're not going to do this for your assignment, by the way. This is just for your own information. But the other thing I wanted to just point out, something you will do for your assignment, is that so far in this lecture, all the pieces of work that we threw into the queue were independent. You could process them in any order and it didn't matter. Something that's very common in a lot of different systems is those pieces of the work, many of them might be executed in parallel, might be independent, but they have dependencies between these two. So here's an example where I wrote some code where I said, okay, let's say I had an API to tell the system, here's a new piece of work. So I want you to do task foo. And then we say, I want you to then do task bar, but please only do bar after you've done foo. So I'm building up this dependency graph that constrain or limit what can run when. So your assignment 2, the final part of it, will be I give you a bunch of tasks like this with the dependencies, and you have to implement a work queue that runs those tasks but respects all those dependencies. And so it can be a little tricky, right? Because like maybe one task finishes, and that means that you can now start running a whole bunch of future tasks that you had already been given but could not start just yet. So this is a very, very common scheduling problem that exists in a bunch of different systems. So that's what your assignment 2 is going to be. Okay. So just a little bit of summary that I probably stated a bunch of times. Any questions so far? Yeah.
It's not clear to me why stealing a task from another thread makes it faster, because then doesn't the work queue still remain empty?
Let's get into it. Let's get into it. Okay. So far in this class, because it's pretty easy to think about, almost all of the code that we have looked at, almost all of the programs, the parallelism comes from doing about the same thing on different pieces of data from a collection. So in the Mandelbrot fractal, it was compute the color of a pixel for all pixels. For many of the other examples in assignment 1, it was like compute the sign of this number, or so on and so on. So all the code that we have looked at kind of had this structure, for each element of the array. Okay? For each task, every task does something different. Later in the course, we'll talk about functional abstractions, which says run the function foo on every element of the array A and put the output in every element of the array B. So this is more of like a PyTorch kind of way of thinking about things. There are other things that you'll see when we get into CUDA and other types of programming. Like there's a little C extension called OpenMP. OpenMP, you put these little pragmas in front of your for loop, and basically this pragma tells the compiler, this is a normal C for loop, but I promise the loop iterations are independent. Under the hood, launch actual threads and execute these iterations in parallel. So like this easiest way to get parallelism in C is just use these little OpenMP kind of things. And when we get into programming in CUDA, it's going to be the same thing. It's like, I want you to run this function foo like this many times, and I want you to run on those arrays. So everything that we've seen so far has been like, let me just give you some arrays or some tensors, and I want you to do the same thing on everything. And so that's one way of programming that we've talked about. The other way of programming that you're probably much more accustomed to is if you want parallelism, you don't describe independent things. You actually create workers and have them do stuff. So here's an example where I actually create a bunch of P threads, or C++ threads, excuse me, in this case. So I am saying, as the programmer, I want you to create these N threads, and this is what they will do. So in the first case, I was thinking in terms of data. For all of these pieces of data, you can do this independently. When we're threaded programming, we think a little bit more like, here are my threads, and here's what they should do. And another way of thinking about programs that's sort of pretty elegant, there's another class of algorithms that, like if you took 161 or something like that, you would think about them in a very divide and conquer kind of way. So the canonical example of that is Quicksort. So can I just quick check? Quicksort is something that everybody has seen? Okay, all right, great. And so maybe just a little bit of review of Quicksort, just I know you've seen it, would be given an array, I want to sort it, and I sort it in a divide and conquer way. And the summary of Quicksort, remember, is I pick some element in that array, the details of which matter for its asymptotic complexity, but for the sake of this class, pick some elements of the array at random, or even pick the first one. And then I'm going to partition. I'm going to move all the elements below less than that value to one side of the array, move all the elements above that value to the other side of the array, and then I'm going to recurse. And that's what you see here. So the recursive calls to Quicksort. So this partition is picking the pivot, and then is picking the pivot and moving everything less than the pivot to the left side of the array, moving everything greater than the pivot to the right side of the array. Now it means that everything on the left side of the array can be sorted, and everything on the right side of the array can be sorted, and recursively we have a sorted array. Okay, just a little review of Quicksort. Okay, so the skill that you're supposed to be building up in this class is if you look at this code, step one in any parallel programming exercise is identify potential parallelism. And where is that in this program? Let's assume that partition is going to be done serially for now. Let's treat that as a black box. Yeah.
The recursive calls.
So two recursive calls to Quicksort. We can do the left side and the right side in parallel. So we're kind of used to this data parallel thinking where we say, oh, we got an array of 10 million elements. Everything can be done in parallel. Here we're saying, hey, functionally we have two things that can be done in parallel. Probably not enough to saturate a big parallel computer with just this one recursive call. But where do I get my lots of parallelism from?
Each of those calls is going to make more calls.
Right. Each of those calls is going to create two more things, and so on and so on. So I have this tree of potential parallelism. So this is independent work. And if I recurse, ultimately, at some point, I get down to a level of the tree where I have a lot of parallel things to do. So this is a recursive algorithm that progressively reveals its parallelism. Unlike this data parallel stuff where I say, here's a million things to do. Okay, so we're good on the workload, right? All right. So what I'm going to talk about now is a programming abstraction that makes it a lot easier to write these divide and conquer parallel programs. And you're going to have at your disposal, and by the way, this is a programming system called Cilk. It exists in most modern C++ compilers today, so you probably can, on your Myth machines, write code like this if you wish. And there's only two changes to C in principle. So typically we think about a normal function call. What we're going to do is we're going to be able to put this little keyword spawn in front of a function call. And then we're going to add one more construct to the language called Cilk. Now let's talk and be really clear about what this means. So what Cilk spawn a function means is please invoke foo just like any other function call would. But unlike a normal function call, the caller may continue executing asynchronously with the callee. This is one of those cases where I want to be very clear about in your mind, does the semantics of what the programming model means, is that clear to you, independent of how it might be implemented? So in normal C, if we call a function, the calling thread of control goes into the function must return, and then the caller continues. In Cilk, if it is a spawn foo, what it means is that the caller can just continue, and asynchronously, foo may run. And then Cilk just says, for any calls that I have spawned, Cilk means that you are guaranteed that those calls have completed, have returned, prior to continuing from this function. So you can think about Cilk as a barrier for all spawned functions. Okay? Questions? Notice that I haven't said anything about C++ threads, implementation, or anything like that. Okay, so this all is clear to everybody. Okay? All right. So you might be thinking, oh, this Cilk spawn foo feels a lot like forking a thread. And the Cilk feels a whole lot like joining a thread. But there's a difference between creating threads and spawning work. You can think about this as there's some work to do, that is execute the function foo on these arguments, and you can do it whenever you want at some future time. That's different from forking a thread, which creating a thread, which says, here is a thread of control. It is now running. It needs an execution context. Processor is running it. Let's see if further elaboration makes sense, but I'm expecting questions soon. So here's an example, my function, that calls foo and bar. And I'm starting to adopt this illustration here on the right, which illustrates kind of the stack or the sequence of execution of this thread of control. Okay? So in this thread of control, there's like part A, the part of my func before the call to foo. Then there will be the execution of foo, then the execution of bar, and then everything after bar. That's just normal C function calls. In Cilk, spawning foo is like creating an asynchronous concurrent logical instruction stream that may or may not be run at the same time. So you can think about spawning foo as more like creating a piece of work, some note that says you got to run foo at some point. And notice what I'm drawing here is I'm showing you the concurrency in the program using my arrows. So spawn foo and then calling bar and then syncing. Notice that foo is spawned off to the side. Bar is actually executed as a normal C function by the caller. That's why it's straight down. And then the sync means that the main caller has to wait for foo to complete before it continues. Does that diagram make sense? And then just check your understanding. I can also spawn foo, spawn bar, and then sync, and notice that the initial logical thread doesn't do anything, right? It just sits there and just waits for foo and bar to get to finish. Yes?
Guaranteed that, say, on like the second example, foo and bar will never run spawn them with this Cilk spawn.
So we should be careful about, I want you to think about this as logical work. So what is true in the semantics is that bar and foo are two pieces of work that can run asynchronously with this. I'm being very careful not to telling you what, like, if there's a thread pool under the hood, what threads are actually going to run these things. But logically, I have 3 logical threads of control here that are defining work that needs to be done and can be done concurrently at the same time.
Copies of their parameters.
For now, just think about it as a shared address space. Just completely shared address space. And then just one more check. Here's spawn foo var fizz. Buzz happens as a conventional C function call. Notice that it's right here on the main thread. And then I sync to make sure all the asynchronous stuff is done before continuing on. Okay. So Cilk says nothing about when this asynchronous work is done, other than it has to get done before sync happens, before sync returns. And so a question to you is this question here on the slide. Is an implementation of Cilk correct? Meaning, does it get a valid answer to the program if I just took out all of the spawns and syncs from the code? If my implementation of the Cilk compiler is take this text string, search for Cilk_spawn, remove it, search for sync, remove it, and then compile the resulting program as a normal C program. Yeah.
Yes.
It is a correct program. And the language was actually intentionally designed for this to be the case. Right? Can you see that? Okay. Now, of course, would it be a correct program if the implementation here would be whenever there was a Cilk spawn, it spawned a P thread to run foo, spawned another C++ thread to run bar, spawned another C++ thread to run fizz, and then Cilk sync was just a join of all 3 of those P threads. That's also a valid implementation. Is it? Yeah. Question? Yeah, okay. Those are 2 valid implementations of this programming model.
There's like no constraints on order, we'll have dependencies, and like we can't guarantee that.
Notice that there's no dependency here between foo, bar, and fizz. The only dependency is that foo can run asynchronously with the main thread, and foo must be done by the time the main thread returns from Cilk sync. Those are the only scheduling constraints. So I could run foo bar fizz sequentially. I could run foo bar fizz on different threads. I could run foo and bar on one thread and fizz on another. Those are all valid potential schedules or implementations of this program. They will all get the same answer.
Would fizz bar foo be valid by that case?
Fizz bar foo in...
If you said spawn, because it doesn't really, would it not really matter?
Because this foo is asynchronous with the main thing. Bar is asynchronous with the main thing. So it must be asynchronous with foo. And if fizz is asynchronous with the main thing, which is asynchronous with bar and foo, yes, they're all different. Do not think about this as like a command buffer or something like that, and I'm pushing things into a command. Yeah, I'm just saying foo, bar, and fizz are all completely independent things that can be scheduled in any order. Just, hey, you better be done with them by the time this call returns. That's the only guarantee I get as the programmer. So I'm just kicking off parallel work, basically. Now the difference is that like these foos and bars, they can be recursive functions and they can actually kick off their own parallel work also. Okay, so here's Quicksort implemented in this programming model. Notice that the only thing I did, more or less, was call spawn. Oh, by the way, there's an implicit sync at the end of the function, so I didn't write it here. But when a function returns, all things that is spawned have to sync at the end of the function. So that's why you don't see a sync here. And the only other thing is I have this like, if the size of the array is sufficiently small, just do it sequentially because at that point, so I don't want any overhead of dealing with concurrency or anything like that. So there's a little bit of a base case there now, but I didn't need to put that in there for correctness. Okay? And now look to see if you can confirm that this is correct. So we start with the main thread. The main thread runs partition, which is a normal C function. Based on the partition, it spawns, well, first of all, it does a normal, it spawns parallel work. So that's the edge off to the right. And then it calls Quicksort recursively on the current thread of control. I could have spawned both of them, but I just decided to do one of them on the main thread. They're essentially the same. Okay. And then that's where I get these two gray boxes. And then we recurse. Inside the gray boxes, there's a partition call, and then another spawn. And so on, all the way down to the leaves of this tree, where the leaves are just calling standard std sort. Okay. And that small little implementation detail in my cutoff. Any questions about this program and the corresponding diagram? Good. Cool. Okay. So the main idea here is just the programmer's responsibility is just to reveal work. And it can reveal it in a recursive way. Okay? It's Cilk's responsibility to schedule these programs. So your goal is to make sure that the recursion generates enough parallel tasks such that a good scheduler can schedule them and get good workload balance. If I don't create enough parallel tasks, there's nothing anybody can do. Okay. All right. And so as I've alluded to, like the simplest possible implementation of Cilk is ignore all of the spawn and sync keywords and run everything sequentially. The other crazy simple implementation is turn every spawn into an actual standard thread spawn and every sync into a join of everything that I've spawned. And that is a valid implementation, but it would be a little bit slow because like the cost of spawning threads is pretty heavy. Remember that demo I showed last week? It was like 300 times faster by using a thread pool versus, okay. So yeah, so this is a little bit much. So what we're going to do is we're going to do what everybody does, is we're going to create a thread pool. Let's say I have a processor that has like 8 execution contexts. At the beginning of the program, I'm going to fire up 8 threads. And all of those threads are going to be just running while there is still work to do in the system. I'm going to go grab the next piece of work. I'm going to go grab a piece of work, and I'm going to get it done. That's the thing here. Right. So all of these spawn calls are actually going to be like adding work to a list of things to do. And we need an algorithm that each of the threads are running that achieves good workload balance and minimizes synchronization cost. Okay, so let's think about an example here. Cilk spawn foo, run bar on the main thread, and then sync. That's what we have off to the side. And just to give some things some names, I'm going to call the asynchronous call the child, and I'm going to call the rest of the main thread the continuation, just to give things some names. So if we only have one core, we have a choice to make. We can either run the child first, or we run the continuation. A normal C program does what? If this is a normal C code, does it run the child first, or does it run the continuation? Runs the child first, because we go into the function call. Exactly. So now let's assume that we have a pool of 2 threads. Okay. All right. Let's assume that we have a pool of 2 threads, and I got ahead of myself. Like, if this was a single-threaded implementation, I just have a stack, right? And what would happen is when I call foo, I push my current frame onto the stack. I go run foo, and then when I return back to the caller. And that's just how it works. So imagine I'm running, in this case, I'm running foo. But while I'm running foo, which is asynchronous with the caller in Cilk, my other thread is just idle, right? So the name of the game here is that thread 1 could be running, bar. It could be running the caller. And so what's going to happen is when this thread calls foo, it starts running foo, and then it puts bar, it reveals its stack to all other threads. And if thread 1 over there is idle and sees that thread 0 has bar in its work queue, thread 1 is just going to rip that out of the stack and start running bar. Or really, it's just going to put bar in its own stack, or its own work queue. Okay? So instead of the stack just being kind of sitting there in the heap and uninterpretable to other threads, what's going to happen is when we spawn foo, we're actually going to create this data record that says there's foo, and there's the continuation, and there's bar. Both of these are in my work queue. One of the threads will take foo, the other thread will take bar. So in this multiple queue situation, every worker thread has a queue of stuff that it's supposed to do next. And if my queue ever goes empty, I'm going to go steal from somebody else. Okay? All right. So we have some options. When I look at this foo and bar, I can either start running, like the thread that actually runs this code, it could either start running bar and put foo on the stack for stealing, or it can start running foo and put bar on the stack. Did I say the same thing twice? I can't remember. I might have, but I think you get the point, right? So running the continuation first is queuing the function call for later stealing. Running the child first is in queuing the continuation for later stealing. This is the same order as a serial program. This is a completely different order. Okay. So it's kind of unclear which one is better. So let's take a look at this program. I have a for loop for I equals 0 to n, spawn, 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 spawn. So the work looks like this. Like I get all these edges off to the right side. Okay. And if we run the continuation first, every one of those spawns is just going to be adding foo 0, foo 1, foo 2, foo 3 into my work queue. And the existing thread is just going to keep running that for loop, because that's the continuation. It just keeps running the caller. And this queue just kind of fills up with a bunch of work. Can you see how that works? What's going to happen if we run the child first? The thread gets to the first foo, spawn of foo 0, and what does it start doing? Yeah.
It's going to start doing the work for that foo call, and it's not going to make more work.
Right. So this thread's going to start doing foo 0, and it's going to put its continuation on its stack. on its work queue. So it says, I'm working on foo0, and the rest of that for loop is the task that I'm going to put in my queue as something I have to do later. So it might look a little bit like this. So in my indication, my notation here is thread 0 is running foo0, and thread 0's work queue has in it the rest of the loop, which I noted there is the continuation of the loop starting at the iteration I equals 1, the next iteration. So I just start doing what the child, and I just shove everything else onto the queue. Okay. Now what happens in this scheme, in this run child first scheme, if I have 2 threads? So what is thread? So thread 0 is running foo. It put the rest of the continuation into its stack. There's some other thread that steals the rest of the for loop, starts running iteration 1, which causes it to start running iteration 1, and then I need, sorry, I made one mistake. And then the rest of the work to steal is the for loop beginning at iteration 2, right? And then if thread 0 gets done, it steals the continuation back, starts running foo2, and puts the continuation with iteration 3 into its queue. Okay. So in the first example, well, in this example, the continuation is just going to be bouncing between the threads. In the other example, the caller just created all of the iterations of the work in its own queue, and the second thread was just going to steal all these little pieces. Okay, this is a good one to talk through in the future, or offline. It's like a good one just to make sure you work through. So at this point, you're like, you're probably not feeling very good about this, because like work's like bouncing around all over the place. But let's think about this when your algorithm is recursive. Okay, so let's go back to Quicksort. And think about what happens if we're doing a run child first scheme with a recursive divide and conquer algorithm. Let's just say the size of the array was, I think, 200 elements. 200 elements, yeah. So the first thing that happened would be, I'm going to call Quicksort recursively on elements 0 through 100. And I'm going to put onto my future queue, I need to do the quicksort for the back half of the array, 100 to 200. So the first thing I pushed onto my queue was quicksort for the rest. And I started working on quicksort 0 to 100. And then what happens next? I have to push 50 to 100 onto my stack, and I start working on 0 to 50. Then what happens next? I push 26 to 50 onto my stack, and I start working on 0 to 25. So all these recursive calls are building up here. Notice that each piece of work that I threw in is smaller than the previous one. So the tiny tasks are down here. The big tasks are up here. So now all my tasks are different sizes because of the recursive nature of this program. Okay. So now let's think about what these idle threads 1 and 2 are going to do. So they're idle, so what are they going to do? They need to still work because they're not making any progress. So now here's a question. There are 3 pieces of work here. Which one should thread 1 steal? What are some thoughts? Yeah, let's start.
Steal from the top.
Okay, so one vote is for stealing from the top of the queue. Really, these are decks, so you can actually steal from the bottom or the top or anywhere, so they're not actually queues. But
I was also going to say top.
top. What is your justification for stealing from the top?
I was going to say, like we saw like earlier in lecture, if you do the big work last, then you could end up having one thread like working at the very end.
Oh, okay, yeah, that's a good reason. That's actually a pretty interesting reason. I actually wasn't even looking for that. There's even a more obvious reason why you want to steal from the top. You all are correct. Yeah.
It's just going to break up into a bunch of smaller chunks again, which the other guy can do.
So this is a big task. This is quick sorting 100 elements. This is a much smaller task, quick sorting 25 elements. If another thread is going to go through the overhead of stealing some work to give themselves something to do, they should go steal the biggest thing and get working on it immediately, actually for both of your reasons, right? So to minimize overhead, it makes sense for me to look at the state of the world and not go, oh, I'm going to take this little tiny thing away from you, but I'm going to go take a big thing from you. So there's the advantage of this thread 0 is always going to grab the next task off the bottom of its local queue, because this is like the same order as a sequential program in some sense. It's also good because you get data locality and a lot of other nice properties. Remote threads are going to steal from the top of my queue for actually two cool reasons. One is the one that you mentioned. If you steal a lot of work, you won't have to synchronize again for a long time. And two, there are actually, if you make sure that thread 0 is only touching this and all other threads are touching the top, there are very efficient data structures that you can use that don't require nearly as much synchronization, actually. Okay? So here, let's say thread 1 steals the biggest item, and thread 2 steals the next small, or sorry, did I get that right? No, thread 2 stole the big thing in this case, and thread 1 stole the medium-sized thing. Yep, exactly. So, and then like things just start getting to work, and now everybody's processing their own jobs. And all of those jobs, keep in mind, are creating recursive calls and now shoving data into the various queues. So now all these threads are independently working on their subtasks, not communicating at all, and actually revealing more parallel work as they go. Okay? So the idea is that the local thread pushes and pops from the bottom of this queue, from the tail. Remote threads steal from the top, so they stay out of each other's way and they steal big amounts of work. Okay. And as time goes on, notice that each of these threads, just by doing the recursion, are actually going to build up their own work queues. And so they're going to have tons of stuff to do. And until one of them goes idle, there is no more synchronization again. So compare this to a single work queue implementation, where every single time I run out of work, I have to go take that shared variable to go get the next thing. Now I just go look at my local, my own local mydiff, my own local queue, and I can avoid synchronization with the other threads. Okay, and let me just continue this thread, this slide out a little bit, and we've worked. Yeah, sorry, I shouldn't have built that. Okay. So does this make sense? Cool. Yeah.
So let's say thread 0 is done with this task and it wants to get the...
So let's say that thread 0 finishes all of its work.
No, that's the current task.
Oh, the current task, yeah.
And now it wants to get the next one, right?
It will just grab this.
So to grab that, it has to make sure that no other thread has grabbed it.
There are ways to be careful because I know that I, thread 0, know that I'm only going to be accessing this side of the data structure. And other threads are going to be issuing the other side of the data structure. There are very fast data structures where you can, that can help you with that. Correct, yes. Mm-hmm. Yeah?
So when thread 2 finishes its work queue in completion,
Let's just say thread 3 goes idle for any reason at all. It gets done, yep.
does it start stealing from 0 or 1?
Great question. So now there are multiple queues, and we have some options. So is it correct to steal from any one of them?
Not necessarily.
Why not? Well, you get the right answer, what I mean by correct. You're actually going to get the right answer. As long as, if you're idle, still work and start doing it. The question is, what's the most efficient thing to steal from?
It would be whichever has the most work.
You could say that there's maybe you should steal from the busiest thing. It turns out that theoretically, asymptotically, it is optimal to randomly select a queue and steal from it. And that's been proven. There are proofs to say that if you just randomly select a victim, you are within a constant of theoretically optimal. So you could probably improve on that, but if you improve on that, you're only improving your constants. And it's actually a little bit trickier because if everybody makes that same decision to steal from the same thread, all of a sudden that steal might get a little bit more expensive because it could be contention. It also might mean that when I look at the system, I'm like, wow, this guy has a lot of work. By the time other threads make the same decision, some of that work might be gone, and you might be stealing from someone that has a very small amount of work. So it turns out that the simplest thing to do is randomly pick a queue that has work and steal from it. So just a few other things that some elegance of this policy. Let's go back to my for loop example that I started this with. For I equals 0 to n. Essentially, this is like work that says for every element of an array, do some stuff in parallel. I'd like you to convince yourself offline that this code that I wrote will sequentially generate asynchronous work. Either the main thread serially spawns all these things, or the continuation bounces back and forth, is constantly getting stolen. So this is what I want you to think about offline. That code there will serially reveal the parallel work, which is actually not good because I have all these threads and I'd like to really quickly reveal all the work. A much better way to write this for loop is actually this divide and conquer while loop, which says, here's an array of n things. Let's recurse into doing the first half and the second half. Then let's recurse into doing the first quadrant, the first quarter and the second quarter, and so on and so on. This allows half the array to get stolen, and then it splits up like Quicksort, and you get parallel generation of the independent work. So actually, if you see, like, Cilk actually has like a Cilk 4 concept in it. So if you go like Cilk 4 I equals 0 to n, under the hood, they're going to implement it that way because it's the scheduler will ultimately be able to create work faster, and you get to running in parallel much faster. It's actually kind of a cool artifact of stuff. OK, so in the last 3 or 4 minutes, I'm just going to kind of give you a quick sketch of the last little piece of this. How do we implement sync? That's the last piece of this. Like, up until now, it's been pretty simple. But what sync means, I have to go check to see if all this work that's been spawned, which might have been stolen by other threads, I need to know if it's complete. So there's some more bookkeeping that I have to do. Okay. So let's think about Quicksort again. Let's think about the for loop again, because it's easier to think about. Let's imagine that we're in some state where I am working on foo 9, someone else is working on 6, 7, 8, or basically at the end of the iteration, and the only thing left is like the rest of the loop, like basically finish the loop and go on bar. So in this case, let's just say that one of the workers finishes. What do you think's going to happen the next time a worker finishes work? Just apply the rules that we've already talked about. The next thread that finishes will go idle. It will select something to steal. In this case, it will steal the thread 0 continuation. That continuation basically says it's done with the for loop. So what happens next? Yeah.
It's going to try to join all of the other threads.
It'll join on all. It needs to join on all the other threads, right? So if this was implemented sequentially, the join is trivial. You don't have to do anything. But it needs to know that everybody's done. Okay. All right. So let's take a look at this. So what I'm going to do is I'm going to say that I'm going to call this all this area before the sync just a basic block, and I'm just going to give it a name. I'm going to give the name A. And then there's this. So this is the sync for all calls spawned within block A, just to give things a name. So what's going on here is I have thread 0 is working on foo 9, and it has continuation here. Okay, it's the rest of block A. And if this item has never been stolen, then what do we do? Like at thread 0, I put this on my queue. If it's never been stolen, I know that nobody else is doing anything related to this. So sync is just a no up. You just continue. So the only thing you have to do something clever on is when it actually gets stolen. So let's think about that. So let's go back to the very beginning here and say, the very beginning, I'm working on foo 0, and the continuation is the rest of the loop for block A. And at some point, the thing may get stolen. And if it gets stolen, Cilk's going to have to keep a note off to the side. So there's this note of here are the things that have gotten stolen from your work queue. Okay. Now what I'm not talking about here is how to manage the locking and unlocking of all these shared data structures. But there's this saying, hey, look, one worker has stolen work that's related to block A, and 0 remote workers have reported that they have finished work for block A. So in this case, this field is now just empty because it's been stolen. And thread 1 has the continuation of block A. So thread 1 starts doing its job, and at some point, So now thread 1 starts working on foo1, and my reference count of spawn things is 2. And so on and so on and so on as more threads steal. Now my reference count is 3. Okay, now some thread finishes some work from block A. Block A has been stolen, so when we finish work, we have to update the done counter. So that means 3 different threads are working on A or haven't worked on sub-work from A. One of those things is done. And at this point, thread 0 will go steal some more work, and so on, and start working on foo3. And now let's get to the very end of that for loop. When we're on spawn 10, we're done with 9 of these things. These threads have no work to do because they're stuck on, they have no work to do. Thread 2 seems to be doing the last iteration of the for loop. When it gets done, it says, oh, that spawn is complete, or that block is complete. And now it can move on to working on bar. So there's just the sync is going to basically has to keep a record of all of the spawns related to that block. Whenever you complete work from some stolen block, you update your reference counts. And whichever thread finishes the last piece of work, we'll just continue on with the continuation at that time. Okay. So this is kind of called greedy join scheduling. It means all threads are always attempting to steal. So they're being greedy. Threads only go idle if there's nothing in any queue. And the worker thread that initiates the spawn. So in that example I just gave you, like the original spawn was started on thread 0, but the spawn was finished up by thread 2 because it was the last thread to do work related to it. So it says, okay, I'll just keep going with this thread of control. So Cilk's pretty elegant. It's actually a fun thing to play around with. The algorithms for scheduling are based on some pretty sound theoretical guarantees, so that if you do some things randomly, you're guaranteed to be within a constant factor of the optimum schedule. It allows you to write divide and conquer programs almost as easily as if you weren't thinking about parallelism. And under the hood, there's a scheduling policy that maximizes locality, minimizes communication amongst all these threads, but still achieves a pretty good workload balance. So this is much more advanced than what you're expected to implement in your assignment too, but I just thought usually people like to know about it. So this is pretty common in distributed systems as well and other things. So cool. All right, we're done, and I'll see you on Thursday.